Hello everybody, by popular demand and multiple requests, today I'm going to go over hash tables. The idea is that we want to have a container class where we could store many items and have a constant time search. And that is that it doesn't matter how big our container is, it's always going to take the same amount of time to do a search for an item, even through radical extremes and differences. So if we were to consider searching in an array of size 10, we're going to complete that search even with a pretty reckless one, like a linear search, in nanoseconds. So making the assumption that it takes 3 nanoseconds to do that search in an array of size 10, now let's expand our data to quintillion. How many zeros do I have there? 18? I think that's quintillion. So now with an array of size quintillion, assuming we've got a computer that is powerful enough to store that many items, it's still going to take 3 nanoseconds, or at least so close to that that it would be hard to measure the difference. So that's a claim that I would imagine many people who know a little bit about computer science would think is impossible, but it is very possible. It's something that we will be able to do. So the concept of the hash code and the hash table is that if you're going to have a database that you can search in, there's going to be some kind of search field. So imagine you might have a database that has employee numbers as the search field, and the rest of the employee information is what we could extract if we were to find an employee with a certain number. So we have that search field and use that as a way of determining where that employee is going to be stored in an array. So given some data element of some kind, it's really just a matter of creating an integer from the search field. If the search field is already a number, we just have to mold it into an appropriate index for the array. If the search field is a string, there are many ways in which you could take a string and turn it into a number, and then again, shift it into the range of values so it could be a valid index of an array. So once that hash code determines where the element is going to be stored, then searching for an element will take that search field, derive the hash code, look in the array at that index, and we should find it there. So that is really all there is to it. It's a really simple concept. The means by which you conduct a search is the same mechanic that we use for determining where that element is going to be stored. So once it's stored, the resulting search using those same mechanics will lead us to the place where we should find it. So it's one of these things that sounds too simple to be true, but it works beautifully with a couple of artifacts, which we'll get to. So here's an example, and for those that are seeing this for the first time, you'll probably be able to predict some potential problems with this. But we'll pick a really easy database and a really easy search field. We're just going to store integer values, some number between 1 and 100. And we'll assume that we're only going to have 10 of these things to store just for sake of simplicity. So we need to take that which needs to be stored in the array and that which we'll eventually search for later. We need to whittle that down into some number between 0 and 9, since those will be the valid indices that we'll have for an array of size 10. And the easiest way to do that is just mod the value, the search field, by 10. So remember, modding, the mod operator, there is the percent sign, is the remainder after a whole number division. So given an array of size n, if you take any number and mod it by n, you'll get a number between 0 and n minus 1, the possible remainders. That'll give us an index. So were we to store 57 into an array, mod that by 10, the remainder after dividing by 10 is 7, so we'll store the 57 at index 7. Modding by 10 just gives us that least significant digit of an integer. If we want to store at 91, then the resulting remainder after modding by 10 is a 1. We'll store the 91 at index 1. And again, you may be predicting some potential problems here. We want to store 34, then modding by 10 yields a 4, and it's at index 4 where that element will be stored. We want to store a 30, that goes to index 0. So it's a relatively easy process. We just need to look at the least significant digit, and that tells us where elements should be stored. Now, if we want at this point to halt adding elements and go to search for something, if we want to search for that 57, we're just going to use the exact same mechanics we used to add the element into the array to search for it. Searching for the 57, that is our search field. We mod it by 10, that'll give us 7, and we'll look at index 7 and there it is. If we wanted to find the 56, 56 mod 10 is 6, we look at index 6 and there's nothing there. So the search will return information to the client to let them know that what they're looking for wasn't there. So relatively simple. But as you may already be thinking, there are some potential issues that might come up with this strategy. And those are collisions that we might want to store something like a 94. And when we mod 94 by 10, this is in the process where we're adding elements into our hash table, we go to look at index 4 and there's something already there. So we have to find a place to put the 94. So the idea of having multiple elements all colliding into the same hash code and trying to find its place in the same spot in the array, that is called a collision. So with hash tables, there's several levels of artistry that goes into the creation of a hash table. One of them is deriving the hash code itself. We're not always going to have integer values that we need to store. Sometimes they'll be complex objects. Sometimes the search field might be a string. So one level of the artistry that goes into creating a good hash table is in deriving hash codes that are spread out evenly across all possible indices of an array, and less likely to have collisions, less likely to have places where they're all trying to go into the same spot. The other level of artistry that goes into this, and this is all going to vary pretty significantly depending on the type of data we're going to store and how big our array is allowed to be, is the way that we resolve collisions. When we get an element that we're trying to add into our hash table and we see there's something already there, how do we find a new spot in a way that is efficient and ends up getting us as close to constant time search as possible? So what I'll propose for this very first one is a strategy that's probably the easiest concept and the easiest to code, and it may be appropriate in certain situations, but it may be the least effective if we just sort of consider all possible hash codes. So this is a strategy in which, if our goal is to minimize collisions, this will handle collisions, but it's not going to minimize them. Our goal in the end is to try to get as close to constant time as possible. The more collisions we have, the further it's going to pull us from that goal. It's something where if you're going to maximize all the collisions, if we're going to take the opposite goal and try to make the worst hash table possible, then we'll usually end up with something that's no better than just doing a linear search through a randomly sorted array. We want to make this as efficient as possible. But this very first strategy, it's usually the first one taught for handling collisions, is called linear probing. Unfortunate name. Linear probing, the idea is that if you want to store something at a certain index and there's something already there, just probe over to the right until you find the first available spot. If you happen to be at the end of the array and in trying to probe over to the right, there is no next index. We just wrap back around to index 0. So with then doing a search afterwards, we'll use the same strategy. We'll look at the spot where we really want to find it, and if it's not there, we'll probe to the right until we do. So again, you may be predicting some possible issues with linear probing, and I'll say that out of the strategies that I'll discuss, globally linear probing may be the weakest strategy, but for certain types of databases, it could be entirely appropriate. So we go to store that 94. We mod our search field, the 94 by 10, and we get an index 4. And we see there's something already there. It's already taken. So we'll probe over to the right. index 5 is open, so we'll store our 94 there. If we want to store a 19, we go to look at index 9. It's empty, so we'll go ahead and add 19 at index 9. We want to store 49, so we mod that by 10. We check index 9, we see it's already taken, so we probe over to the right, but we're at the end of the array, so it's going to wrap back around to index 0. But that's taken, so we'll check index 1, and that is taken. And the first open spot that we find is index 2, so we'll store our 49 there. And here you're going to see, if you didn't predict this problem occurring, here you'll see it fleshed out. We now want to store 29. Index 9 is taken. Probe over to the right and wrap around. Index 0 is taken, index 1, and index 2. That 29's got to go all the way to index 3. It's pretty far away from the first spot where we really wanted to place it. If we want to store 20, index 0 is taken, and it has to probe all the way over and to index 6 and store it there. So you can see, again, we really want that 20 to be at index 0, but because of these collisions, we have to move it pretty far across the array to find the first open spot for it to go. So the issue with linear probing is, again, we want to be as close to a constant time search as possible. We really want to have it so it doesn't matter how big the database is, how many elements we have stored. It'll always take or do relatively the same amount of work to search for something. But with linear probing, with each collision, it makes it more likely that there's going to be another collision by means of taking someone else's spot. And you could see that if we wanted to search for 20, then we'll first check index 0, and it's not an index 0. There's something already there. So then we'll check index 1, and then index 2, and then index 3, all the way up to index 6 before we find it. And this is all of a sudden starting to sound a lot like just doing a linear search. This doesn't sound like constant time. This is something that's definitely linear time. We're doing a good amount of work here with this particular simple database. But as mentioned, there are certain situations where linear probing can be perfectly acceptable. If you can guarantee you'll have very few collisions and there's sort of padding in between values, then this can be a successful method. And it's certainly the easiest concept and easiest to write. But that's going to wrap up this introduction. And in the next video, I'll talk about much more effective methods for resolving collisions.